Now let us take an example wherein your y1 is equal to r1, y2 is r2, in place of y3 you have c3, and y4 in place of y4 you have c4. Now in this case, if you use this transfer function, because this is a generalized transfer function, now whatever value we put in place of y1, y2, y3, y4, we just have to replace them, or we just have to take those values and put them in this transfer function equation. So this transfer function equation I have written over here. Now in case of this example, G is equal to 1 by R and Y is equal to CS, because this is capacitance, right? So Y will be CS. Now your HS will be V0S by V in S, the transfer function. You put the value of G1 and G2 and CS values. So it will be G1 into G2 divided by G1 into G2 plus SC4 into G1 plus G2 plus SC3. Is that okay? Just have replaced these values in this equation. And now you see at S equal to 0, your HS is 1. What does that mean? At 0 frequency, you have certain transfer function value. So it is a characteristics of low pass filter. This is your low pass filter. Let's not, okay. Ideally it would be like this. So ideally it would be like this. Practically it would be like this. So let us take this as an low pass filter value. So at omega equal to 0, this is your omega, you have some value, that means it is a low pass filter characteristic. So you can say that this is your low pass filter. Okay. And at infinite, S equal to infinite, you have HS equal to 0, which is true. If your frequency is increasing, you have nothing as output. So it is basically a low pass filter. Okay, just using that generalized circuit, we have made a low pass filter. Now if you want a high pass filter, what you will do? You will interchange the position of C and R. Place capacitance in place of resistances and resistance in place of capacitances. So you will find a high pass filter. Okay. Now let us assume your R1 is equal to R2 is equal to R. Okay. If you take this condition, you will see that your transfer function is, which was this one, will be something like this. Okay. Now your transfer function will become something like this if you define RC3 as tau 3 and RC4 as tau 4. Okay, this is the definitions. You are just replacing those values and finally you get a transfer function similar to this. Now I have said there are two problems associated with a practical filter. One is the ripple, another one is the transition band. One is the ripple that you see in the transfer function as I have shown here. So you have ripples present here and here, and you have a transition band. So your goal is to reduce the ripples as well as reduce the transition band. Now in order to reduce the ripples, we use a special kind of filter known as Butterworth filter. And in case of and if you want to reduce the transition band, we use a filter called Chebyshev filter. Okay. Now if you see in this case, in generalized filter case, you have a transfer function. Okay. Basically this filter is also known as Butterworth filter. So we will discuss Butterworth filter later as well. Okay. But just as we have encountered a filter of similar kind, I am just mentioning the name. Now if you want this ripple to be very less, what you will do? Your transfer function should be, the derivative of your transfer function with respect to omega should be equal to 0. then you can say that if your dH divided by d omega is equal to 0, you can say this is a constant value, no ripples, no change in this transfer function, right? So this condition is known as maximally flat filter. That means maximally flat means it's completely flat, no ripples are present. So for maximally flat filter, this derivative should be equal to 0, tend to 0 or equal to 0. So if you differentiate this function and put that this differentiation is equal to 0, you will find a condition where tau 3 is equal to 2 tau 4, which gives you C3 is equal to 2C4. Now for this condition, if your C3 is equal to 2C4, you will get a maximally flat filter. That means you will get very less amount of ripple. There might be some ripple, but it's almost flat. Okay, theoretically it should be completely flat. There should not be any ripple, right? So you will get, after replacing those values, tau 3, tau 4, you will get hj omega is something like that. So you get a transfer function which is similar to this, and your pole will occur at minus 3 dB point. So it is known as minus 3 dB gain. Okay, so this is one condition that you find from this transfer function, that for the minimum amount of ripple, this is the condition that you have to hold in case of the generalized filter we just have seen. In case of this generalized filter, or better to say this filter, because we are considering this filter currently, right? So you will get a pole at minus 3 dB, which will be equal to something like 1 divided by root 2 RC4. So you will get a 40 dB decrease in transfer function, 40 dB per decade decrease in transfer function for this kind of low pass filter. However, remember, this is according to Borde's approximation. In practice, this will be something like this. Okay, so this point is your 3 dB point. So your first pole occurs at minus 3 dB. With this condition, we found that your transfer function is something like that. And if you see the transfer function here, how many s you have? 2, because it's s square. So if you arrange it, you can arrange this particular thing as s plus a, s plus b, something like this. So you will have 2 poles, and both the poles are occurring in the same point for this condition, and that's why you get a minus 40 dB per decade decrease. So you are close to a ideal filter. Previously it was 20 dB. If you see the normal RC filter, it was 20 dB. Now it is 40 dB decrease. It was minus 20. Now another minus 20. You have minus 40 dB per decade decrease. Okay. So this is a generalized filter. Now we use also biquadratic function. Now what does that mean? So your transfer function can be written as similar to this: a2s square plus a1s plus a0 divided by s square plus b1s plus b0. This is a general form of a transfer function. Now for high pass filter, the transfer function should look something like this: k divided by s square plus omega 0 by q into s plus omega 0 square. Okay, what is q? Q is known as quality factor. So the damping factor can be expressed as 1 by 2q. So your 1 by 2q is basically k. This k is known as damping factor. What does that damping mean? Damping means, say you have a step function. Okay, you applied a step function to the input of a system, and in the output you will see that the output is not exactly what exactly looks like the input, which should be. Rather, it looks, if this is the ideal thing that you are expecting, but it looks something like this. So there is a kind of oscillation in the beginning, and then it slowly follows the expected curve, expected output curve. Now this damping factor will decide how fast this will follow the expected curve. Okay, so somewhere you will find this k is also written as zeta. So that's why this k is known as damping factor. Okay, so this damping factor and quality factor has a relation which is k equal to 1 by 2q. Okay, so this is a typical function for an high pass filter. For low pass filter, this will be k s square divided by s square plus omega q into s plus omega 0 square. Now for band pass and band reject, you will also get similar expression as it is shown here. So there are some other expressions as well for high pass and low pass as shown here, but mostly we will use these 4 types. Okay, now as a designer, my intention is to make a transfer function similar to these values. Okay, so you have a biquadratic function for each of them. In fact, you can use even bigger transfer functions, as I said, polynomials, right? It can go up to say s cube, s to the power 4, s to the power 5. But the problem is, as you increase the s, this each section will increase, right? For quadratic, it is s plus a, s plus b, and if it is s cube, you'll find another s plus c, then another s plus d. So similar to this. Now each section corresponds to one such circuit. So you need one such circuit for each section. For example, here there was only one such section, 1 plus s, or you can write s plus a. For each section you need one such circuit. So if it is s cube, s to the power 4, s to the power 5, you will find s plus a, s plus b, s plus c into s plus d, and so on, right? So for each section you need one such thing. So what does that mean? You are improving your characteristics. Definitely you are probably imposing 5 poles into a single point, and this will give you 100 dB per decade decrease. But as you increase the sections, cost associated with the filter will also increase. Now there the problem lies. If you have money, I can make this kind of filters. But if the client comes with a budget, that this is my budget and I want this filter, then you have to say, in this budget, this is what you will get. If you want even sharper cutoff, you need to spend more, because each section of these will take some space in your silicon chip. Ultimately you need to lay down all these things into a silicon chip, right? Now in this silicon chip, each micron matters. Now if you increase this type of sections, you are actually taking a space in that silicon chip which has millions of MOSFETs, and this again will have a different design issues. So it is not like that you can increase as much pole as you can. Theoretically it is okay, but in practice this is not possible. That's why we try to make everything using this biquadratic function only. This is a standard one. Okay, we will use 2 sections, but if we get a very good filter using that 2 section, then why should we go for higher? Because anyways, if I put high number of sections, then it will take space in the silicon chip, and in the silicon chip it's really very costly, right? For each micron matters. As I said, you need a very small chip. That's why the cost issue comes into the picture. So you should understand while designing. That is where the design part comes. Otherwise, there is no requirement of design. So here I am not designing anything. I am giving you an analysis and idea of different design conditions. Okay. So the objective is to make a transfer function which will follow this kind of standard transfer functions, and you get your omega 0 and q value from there. Okay. Now say for the low pass filter, we have R1, R2 and C1, C2, and we also have put some certain amount of gain. So you have a gain function also associated with that. So this resistances will decide what gain is associated with your filter. So you have a transfer function similar to H0 divided by S square by omega 0 square plus 1 by Q S by omega 0 plus 1. Okay. Now this H0 is nothing but the gain function that you are getting. So for this section you have a gain equal to 1 plus R3 by R4. Okay. So this is the typical low pass filter that we are taking now into the consideration. Now if you put KCL at nodes, just like the other case, the generalized case, you can easily find your transfer function is something like this: S square, S and 1. So it is a biquadratic equation. Anyways, this R1, R2, C1, C2 is the constant value that you need to figure out which value should you should use, but it's something similar to the function that we have seen, k divided by S square plus omega 0 by Q S plus omega 0 square. So it is of this form. So you have your transfer function ready, and you can very easily find if you compare it with the function that I just have shown you. Then you have omega 0 and Q value. Okay. Now let us choose this R1 equal to R2 equal to R and C1 equal to C2 equal to C. Then you will have a transfer function similar to this one. So in this case you have omega 0 value is equal to 1 by RC and Q value is equal to 1 by 3 minus AV0. Now if you see here, if your AV0 becomes more than 3, your Q will become negative. Now in that case you will find that it is not following the margin, phase margin that we already have shown you, right? A phase margin case, your phase margin should be for stability, what should be the condition? If this Q portion becomes negative, then your system will no longer be stable. So for stability you have a condition that your gain should be less than or equal to 3. Even if you put a gain function over here, for low pass filter to function properly with stable values, you have a limitation of gain. You can't use any gain and put this filter into the circuit, then there will be a trouble. So what I wanted to say is, it doesn't mean that you use a gain or use an op-amp and just put any value of gain and then use the filter. That is not possible. You have to take care of all these things. If your gain is becoming more than 3, you will reaching in the unstable zone. This is nothing but the pole is not in the stable zone. Simple as that. Okay. So this is another example. Now similarly, we also have another type of filter which is also an biquadratic filter or biquad filter, which is made out of OTA. OTA means operational transconductance amplifier. Now operational transconductance amplifier mean I already have discussed there are different types of amplifier that is possible: current amplifier, voltage amplifier, and then there is transconductance amplifier where your output is current and input is voltage. So there is also operational transconductance amplifier, which also is known as GMC filter. Why GMC? Just in a while we will see. Now in this case, for this kind of amplifiers, the gain GM, capital GM is equal to GM into K. Okay, GM is the transconductance. Okay, and you have a expression of GM. Now one thing you notice, in case of this operational transconductance amplifier, the symbol is something like this. It's not a triangle, it's kind of a trapezium. Okay, where this side is higher and this side is lower. It's not similar to an operational amplifier that we use. It is not triangular. The symbol is also different. Now for that purpose you also use a bias I0. Previously also in case of diff amp, op amp, everywhere you need a bias. Here also you need a bias. Now this function GM is equal to small gm into K. Now say K equal to 1. If your K equal to 1, your capital GM will be equal to small gm. Now we also know the value of small gm, which is nothing but root over 2 beta dash omega by L into I bias. Okay. Now let us design a kind of filter wherein you attach a capacitance and also connect the negative terminal with the output as a feedback. Okay, so this is say one filter that you have designed. Now in such a situation you will see that your V out is equal to I out into 1 by Cs. No current flows inside the operational amplifier, so there will be no current in this direction, no current. So all the current will flow through this C. So your V out will be I out into 1 by Cs. Similarly, your I out will be nothing but GM into the differential input. Differential input is V in, and here you have V out because this is shorted. So your V in minus V out into GM will be your I out for the OTA, because it is operational transconductance amplifier, right? So from there you will get V out by V in is equal to something like 1 divided by 1 plus CS into 1 by GM. Simple calculations. Okay, if you do it by yourself you will find this type of results. So for you will get a pole omega 0 is equal to GM by C. So you have a pole of this kind. Now this is your transfer function. This is how it will look like. This point is GM by C. Now if you want to increase your bandwidth, say you want to make it like this. So if you want to increase your bandwidth, either your GM value should be high. Now if you increase your GM value, what is required? Either you increase W by L, which also has a limit. You can't get any value of W by L because there is a technology limitation. How much W by L you can expect? 4, 5, 6 maybe. So there is a limitation. Or what you can do, increase I bias, the bias current. Now if you increase bias current, you are going to lose gain, which is also not desirable. So definitely I bias increasing is also not a feasible option. Another thing is you reduce the value of C. Now reduction of the value of C also has a limit, because you are using it in a IC integrated circuit. You will find there are a lot of parasitic capacitances sitting. If two lines are going inside the two connections are going parallelly in the IC, you will find it will also create an capacitance, parasitic capacitance. Now if your this C value is very low, these parasitic capacitances will come into the action, and you will see they are actually parallel with this C, so they are increasing the C. So you can't go beyond a certain limit, and moreover your whole system will become unstable if it is very low, because these parasitics will start dominating, and parasitics you don't have any control on this parasitic capacitance. So usually these OTA or GMC filters are for low frequency range, say maximum up to 1 megahertz, 0.5 megahertz. But these are very popular because it doesn't require much components. So you can make a small chip using this kind of filters. So these filters are mostly used in low frequency domains, especially in audio filters. in audio filtering circuits, you will find OTA filters are used. So these are mostly for low frequency operation. However, for video filters you can't use, because video starts in megahertz, with 60 megahertz or so. So it anyways can't go in 60 megahertz. But theoretically you can. Theoretically you can put any value, GMNC, and you will get gigahertz even. But in practice it is not possible. However, these OTA filters are very much useful for low frequency application. You will find lot of commercial application of this kind of OTA filters. Okay.